remember for today's lecture. First of all, when we proved Gauss theorem egregium, we just needed to prove that there was a formula involving giving the Gauss curvature in terms of the first fundamental form and its derivatives. Okay, so this was quite complicated, but this was a special case that could come up out of the proof. Second reminder, if we take a curve parameterized by arc length, then actually we wrote down the system of differential equations locally, in a chart for which tells us when this curve is a geodesic. Okay, so that's if I didn't make mistake, that should be the thing. Because today's lecture basically we want to mix these two things and to use geodesic to reach the point where actually we'll always get the first fundamental form in some sense in a canonical form. So with these two properties satisfied. So how do we start? Actually now also a picture would be again useful. So we are on our surface. So now we are going to construct a system of a special chart on the surface. Starting from what? Well, starting from, suppose that you have actually one geodesic gamma. Okay, and of course this gamma has a parameter. So actually let me call it gamma V. Okay, we don't know exactly how big the parameter space is, but for sure for any point there is and then for any vector this V varies on minus epsilon epsilon, so at least there is an open interval for which such a geodesic always exists. Suppose actually we also give a name to some kind of central point, gamma of 0 is equal to P, so basically we are going to construct charts around a given point P. But now, so you see, of course, I'm looking for a chart for a surface, so I have only one real parameter. So where do I put the second one? And in some sense, of course, I want to go transversally to this one. Okay. So what do I do? Basically, for any point, gamma V, I take the orthogonal direction to gamma dot. So I have the tangent vector to the geodesic at the point V, and I take the orthogonal direction. Okay. Now, in fact, just a thing of notation. So now I call gamma V of U what? Exactly the geodesic. And you see, I can say the because I know the uniqueness part of the theorem for the existence. So now I have a point, gamma of V. So is the unique geodesic such that what? So I need to impose passing through a point with a given direction. So gamma V of 0 is gamma of V. Okay, so it passes through the point gamma of V at time 0 for its time, and gamma V dot at 0 is this orthogonal direction, is orthogonal to gamma dot of V. Oh, but now, sorry, maybe this is a kind of a bad notation. This is D in du, because this dot symbol now can be called, and this is D in dV. Okay, one is the tangent in the direction of V, and the other the tangent is the direction of U. Okay. So basically, so see, geometrically, what am I doing? I'm covering, or at least I hope I'm covering, the whole neighborhood of this point with one geodesic, which I can think of it as kind of the skeleton of this thing, plus all these kind of orthogonal lines. Okay. So my hope is, of course, in this way, since, again, I should be a little bit careful about the domain of definitions of these curves. So for any V, there exists, what does the existence theorem tell me? That there exists a small interval, but now the point is moving. So the domain of definition of the geodesic gamma V depends on V. Okay, so it's always positive, but I don't know how big it is. Okay, there exists an epsilon V such that gamma V gamma V is defined from minus epsilon V to epsilon V to S. Okay. But you see, now suppose I'm taking the point P. This will correspond to some choice of epsilon 0. No? The P corresponds to V equal to 0. So epsilon 0 is something, and then everything is continuous. This is actually something one should check. In the proof of the existence and uniqueness theorem for geodesics, everything is continuous on the dependence of the initial data. If you change, so when we say if you pick a point and the tangent direction, then there exists a unique geodesic defined over minus epsilon passing through this point. Then I have two parameters. I have the point and the tangent direction. Basically, but the theory of differential equation tells us for this kind of systems, u double dot equal and v double dot equal, that if I move the tangent vector continuously, and if I move the point continuously, the domain of definition moves continuously too. Okay, so there are no jumps. So if at time 0, if for v equal to 0, I have some domain of definition, let's say minus 1, 1. Okay, then I'm sure that this will stay positive at least for a small intervals of v. Okay, it doesn't go to 0 or doesn't jump. Okay, this is important because, of course, now I want to construct a map from a domain of R2 I want to construct X of UV, which of course is just going to be, as a map, gamma V of U and now let me just say on a suitable domain open of R2, okay, which of course contains the origin. Okay, because of course I'm picking V equal to 0 is inside my domain because it's the point P, and U equal to 0 again is always contained here because everything is normalized to be the central point of the thing. Again, is this so the problem is this a chart? And then later, of course, the answer has to be yes, at least for small values of U and V. So why? So claim X is a chart. Of course, that means possibly by restricting the domain. Okay. So why is that true? I mean, of course, it's smooth, it's everything. The only thing we need to prove is the famous third condition about the differential, whether the differential of this map is maximal or maximal rank. Okay. So what is the differential of this map? Now, what do we know? Let's just rephrase what we know. XU, so let's look at, so we need to prove that the vectors XU and XV are linearly independent. Okay? At least somewhere. So, what do we know? What is XU at the point 0, 0? Well, this is the derivative with respect to U and then evaluated also at V equal to 0. So that means it's this this famous vector that I didn't give name to, but it's computed on the curve gamma, and it's orthogonal to the tangent to the starting geodesic gamma. Okay? Very good. And what is xv of 0, 0? Well, the opposite in some sense. So now I'm taking the derivative. So I can, since this is derivative with respect to v, I can put u equal to 0. But that means I'm on gamma. And then I compute the derivative. But then I get gamma dot. I get the tangent direction to gamma. Okay? That's what this is another way, it's just a rephrasing of those conditions. In particular, they are linearly independent. They are orthogonal. Okay? So they must be linearly independent for sufficiently small by continuity, no? of the solutions of the geodesic equation with varying initial data for sufficiently small u and v. But of course, what is the problem? The problem is that we know that at time 0, at zero they are orthogonal. We know nothing more outside 0, 0. I mean, we can just claim linearly independent, not orthogonal everywhere. Okay, they will move. If I start, you see, if I draw them on the curve gamma, of course I'm imposing conditions. So on the curve gamma, I know the orthogonality condition. But if I put here, if I ask what are these two vectors here, well, this in one direction there will be one curve passing through this point and the other curve passing through this other, in this other direction in the two variables, and I have no idea whether they stay orthogonal or not. In fact, it would be a miracle. In fact, it almost never happens. In fact, it will happen only in one case, essentially. Okay? But this is enough to claim that we have a very special system of coordinates. And in fact, these coordinates are called, so the charts constructed in this way, every time you have something and you construct this type of charts, you will call X is called a geodesic chart. Okay? Very good. So now comes the key property, because the key property of this chart is that proposition in geodesic charts, let's compute the first fundamental form. And I claim that E is equal to 1 and F is equal to 0. Okay, so this is the famous system of coordinates which puts the first fundamental form in a very canonical form. Okay. Okay, let's prove it. Okay, so what do we have? Let's look at the moment for E. So okay. Of course, I don't know much I mean, these are claims for, I mean, E is equal to 1, F equal to 0 everywhere. Okay? So that's the delicacy of the proposition. I mean, not along gamma. Along gamma, you will see it's basically the construction. We have constructed in such a way that these are orthogonal, and the curve gamma is a geodesic, so it's parameterized by arc length. So it has. Okay. So, well, okay, forget. So the point is what's happening outside gamma, really. Okay. So what is E is, of course, the norm squared of xu. How do I compute xu if you want? I can take the curves given by v equal to constants and look at the tangent vector to these curves. Okay, so what is xu is precisely this. I fix v and I move u, and then I look at the tangent vector to this curve varying u. Okay, and I'm asking what is the norm squared of its tangent vector. I fix v, and I look at the curves x, v is equal to a constant, let me call it v naught, okay? So I'm looking at the curves x of u v naught. So asking what is E means, can you compute the tangent vector to this curve, the norm of the tangent vector to this curve? Okay, so let's go in the picture and see what are we doing. We are fixing v equal to something, and we are looking at the curve when u is changing, okay? But actually, I forgot to put here the only important thing now. Because when we say the unique geodesic, such that okay, we always look at when we solve the system, if we are proving the existence of a geodesic by solving the system we wrote last time, u double dot equal, v double dot equal, we are taking the system of a curve being a geodesic if it's parameterized by arc length. Okay, so what I get is automatically parameterized by arc length. And actually this is the only important thing now, because I'm looking for the norm of the tangent vector to these kind of transversal curves. But these are parameterized by arc lengths, so E is equal to 1. Okay? That was the easy thing. Let's go for F. How do we compute F? Now, F certainly is equal to 0 along the curve gamma, because F is what? Is the scalar product between xu and xv. But on the curve gamma, meaning for u equal to 0, no? For u, which means on gamma. No? On gamma, we know xu is orthogonal to xv, because we constructed it this way. So, F, this means what? That F of 0v is equal to 0 for any v. Okay? Now, let's take, we already know that E is equal to 1. So let's go back here to the system. Which kind of equations does the curve satisfy? The geodesic equation satisfies. So let's see which one is the good one. Now we let V move, and we know already that E is equal to 1. So now my claim is that the system, the geodesic system implies also, this union E is equal to 1, now if I put E is equal to 1 here, of course many terms disappear, but this implies that actually the F du is equal to 0 along the geodesic. Okay. Now, let me remember why. If we pick E is equal to 1. Suggestions are welcome. Huh? So, if I put E is equal to 1 here, where do I get Fu equal to 0? Of course, I want to look at the first equation. That's where Fu appears, no? But now, how do I isolate Fu from there? If I put V equal to a constant, everything dies. What am I doing here now? I'm taking okay. No, in fact I said something wrong because I think it's better to look at the second one. We have to just to rephrase everything. So I'm looking at the curves parameterized by U as the geodesics. Okay, so that means in this language, U is equal to T. Okay, I'm fixing V, and then I'm moving U. But U is what I really should call T. Okay, U of T. So actually I should go here, but if I'm fixing V, of course this goes away, this goes away, this goes away, and here, and this goes away too, because E is equal to 1. See, here this dies because V dot is 0. And this dies because EV is 0. Because E is equal to 1, I've already proved it. Okay, so on the right hand side I have 0. And here this dies because V dot is 0. And here I'm left just with the derivative of F. Of course this cannot be 0, otherwise the curve is not moving. I'm already on the curve V dot equal to 0. I'm fixing V and U is changing, so this one is non-zero, and here I'm left with the derivative of F times something which is non-zero equal to 0. Do you agree? So this means that F, the derivative of F, has to be 0. Okay? Very good, so we are done. We are done because we have a function which is 0 at some point, at the points U equal to 0. It actually does not depend on U. Okay? Of course, the combination of these two things implies that F is equal to 0 everywhere. Okay? Very good. Okay, I hope we will see this construction in complete generality. This has nothing to do with dimension 2. I mean, this kind of system of coordinates can be constructed everywhere. And of course, they are particularly nice because they are also geometrically very nice. I mean, they are constructed using the whole geometry of your surface. So now, before making examples and computations about geodesics, let me show you a very nice application, immediate application of this construction. Or can I erase this one? In fact, we can classify immediately surfaces of constant Gauss curvature. So you remember we proved Hilbert-Lieberman theorems, Gellet, Lieberman, and so on. These were classifications of surfaces under various types of hypotheses. But of course, the simplest question one can ask is, can you tell me which are the surfaces with constant Gauss curvature? Okay, that's by far the most obvious question you can ask. okay, when you start classifying surfaces in terms of curvature, okay. You know some models, something it has already appeared. If you look for something with zero Gauss curvature, well, you have a plane, but you know already that you have also something else, no? The cylinder, something else. If you're looking for positive curvature, you have spheres, okay? For negative curvature, we have never actually seen anything constant. We have seen some examples of surfaces which have negative Gauss curvature everywhere, but not constant. The catenoid, the helicoid, you can build many other things, hyperboloids, okay? But not something which has constant Gauss curvature. Okay, and then of course the question whether it's constant or not, it's interesting. You say, okay, but so let me first give you an example of something which could be what we would call the model. So, example of a surface of constant negative Gauss curvature. Okay. Well, so you pick. I mean, the analytic part is a bit strange. So pick, of course, here in this language, I'm thinking of a non-zero number. So actually, we can construct a family when a is varying. Define f of u, so I define this function as the integral between 0 and u of 1 minus a squared hyperbolic sine squared of at 1 minus to the power 1/2 in dt. Okay? Okay, calculus, you prove this function actually exists and so on. So, now you look at this curve. Look at the curve u going into f of u cosh of au. Okay, so look at this planar curve here. Okay. So first observation, this curve here is actually, this is just the famous, I mean, this is immediate. It's parameterized by arc length. This is immediate just because of the relationship between cosh squared and psi squared. Okay, so without even doing much effort. And now rotate this curve around the x-axis. Note that I can do it because this curve here never touches the x-axis. Okay, y is never 0. Okay, cosh. Okay, I put a positive function there precisely to stay away from the x-axis. Okay, so I can rotate it without creating troubles of vertices and so on and cones and blah blah blah. Okay. So actually now I can write down the surface obtained in this way. Now it has two parameters. One is along the curve and the other is the parameter of rotation. Okay. So this is completely general. So every time I play this game, I will end up with something like this. It's f of u. That's the one I'm not touching because it's the axis of revolution, and then I take cosh a u. But this, and now it's time cos v. So the v parameter is the angle of rotation. No? So that's always the same game. We pick cos v, and then again cosh a u sine v. Okay, since we have not made many exercises and many examples, let's compute everything. Let's take it as an example. So as an exercise. So of course, how much is xu and xv? Now, probability of making an error of computation is very high, so please double check with me. So this is of course, so xu is f prime, which I know. Okay, it's all this mess. So let me just call it f prime. I don't rewrite what it is. Then how much is the derivative of cosh? A sine. Okay, this is the only difference between putting this hyperbolic thing. So it's a sine au cos v, and then a sine au sine v. While on the other, on xv, what do I get? I get 0 minus cosh au sine v cosh au cos v. Okay. So let's compute the coefficients of the first fundamental form. Actually, this time I'm breaking my rule. I mean, I said when we do this kind of exercises, you switch off your brain, you do all the computations, and then you turn it on at the end. But actually, this is probably the only case I know where it's better to keep it on. Okay, I'm not going to compute the second derivatives, the normal vector, that's what I mean. Because if the question is compute the Gauss curvature, well, the simplest way is to, by brute force, xuu, xuv, xvv, n, blah, 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 e, f, g, and then you put everything together. But actually, the whole point of this lecture is actually to use another trick. Okay, so let's try to use it immediately. So let's stop for a moment and compute immediately the first fundamental form. Well, I spoiled the surprise. I mean, so E is equal to 1, because as everybody remembers, cosh squared minus sine squared is equal to 1. I mean, everybody should just remember the difference between the usual trigonometric functions and the hyperbolic functions. And what is f? That's, you don't have to remember anything, you just do it. And f is equal to 0. So you see, actually, in this way, we have already fell into the category. I mean, actually be careful, nobody is saying that this system of coordinates is the system of geodesic coordinates. You see, we have just proved that geodesic coordinates satisfy this. Nobody has ever said anything like the converse, okay? In any case, we are here. So now, this is probably the only situation where actually this formula is easier. I mean, the egregium formula, let's call it, is easier than xuu, xuv, xvv, n, blah, 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 and so on. Okay, so, and how much is k? Right. Okay. Now a little bit of, so this of course it's a very important, actually of course for this reason this is called, this surface, when A plays a little bit the role of the radius of a sphere, no? What is the positive, surfaces of positive Gauss curvature would be, for example, spheres of radius r, and then you get the Gauss curvature is 1 over r squared. So this is kind of, okay, the dependence is not like a 1 over a squared, but it has the same role, no? I mean, the Gauss curvature is changing depending on a. So, for these reasons, this surface is called the pseudosphere. It's kind of a sphere of negative curvature. Okay. Now, so this is a very interesting example. So one should wonder, how does it look? Okay, now there are many ways. So how does it look, a sphere of negative curvature? Well, in fact, it has nothing to do with a sphere, the picture is. Okay, so I mean, the only analogy is having negative constant Gauss curvature. Okay, so if you draw, so the first, of course, everything boils down to drawing this curve, because once you draw this curve, you are just rotating along the x-axis. So how does this curve look like? Well, the point is that it looks like this. So you see that for u equal to 0, this function is actually 0. No? You're integrating between 0 and 0. But then you are actually putting 0, comma, cosh 0. Okay? So for u equal to 0, which corresponds to x equal to 0, you are starting somewhere positive. Okay? 1. And then, well, then actually you ask your, I mean, you do it as a calculus exercise, or you ask a computer to draw it. It really looks like this. Okay? So when you rotate it, eventually, now it's impossible that I get a symmetric picture, but it will look like something like this. Okay? And in fact, you can take pictures from everywhere, okay? So, just one historical comment. It's kind of strange. You see, now you start seeing many examples of this phenomenon. When study curves, there are curves which are more important, more into solve the very natural variational problems. Like the catenoid is the surface of revolution of the catenary. I don't know if Zach mentioned this to you. So and the catenary was there, actually when the catenoid was discovered, everybody knew the catenary since at least 100 years. Why? Because the catenary is the curve which solves the famous problem of how does a wire, the shape of a wire when you, in gravity, with gravity, you take a wire and you hold at the same height 2 points. So actually this, and it was not, again, you know, I like a little bit of history. This was a kind of one of those challenges. Before email and archive, mathematicians were challenging them by sending, so somebody was writing to another one, I mean, Bernoulli was writing to Leibniz saying, I know how to solve this problem. Do you know how to do it? And the other was, of course, was taking 2 years to answer. And then, of course, the answer was always, yes, of course, I know. And then they start discussing who was right, who was wrong. In fact, even before that, before calculus, this was actually the way people were finding jobs. You see, the job market has improved a little bit. In the 16th, 15th century, if you wanted to be a professional mathematician, the only thing you could do, at least in Europe, was actually to go, so every court had a scientist, actually what we call a natural philosopher. So if you wanted to survive, you had to go to the mathematician in charge of the court of Florence, challenge him, and with a set of problems to show that you were better than him or her. Well, actually, I don't think it has ever been a woman at that time. Okay, so if you succeeded, so this was a public event, if you succeeded, this guy was fired and you take the job. That was the way. It was a very nice way to. So later in times, this became just by mail. No, I challenge you. No, Leibniz was challenging Newton. Newton was challenging Bernoulli. We know all this kind of this exchange of letters. No, so this was a famous one because I don't remember who challenged who, but this was then became a famous problem. What is the shape of a wire in gravity if you hold 2 points? And actually, Galileo, which was great for many reasons, but actually he wrote a book saying that, of course, the solution is the parabola, okay, which is wrong. I think it was one of the Bernoullis or something who actually find out that actually this curve is a bit different. Of course, it's very similar when you draw it, but it's called the catenary. So you take the catenary, you rotate, and you get the catenoid, okay, which you have seen in the minimal surface part of the story. This has a very similar story. I don't remember who challenged what, but the problem was here, it was about the curve itself. You see, everything boils. The little miracle here is always that if you find an important curve, you rotate it and you get an important surface. This is, of course, it's a meta theorem. There is no. But this curve here is called the tractrix. So the curve that we are actually rotating of this shape is called the tractrix. And I don't expect you to know Latin, but this suggests which kind of problem this is solving. And this is solving the following problem. Suppose that you have, I think it was set as the problem of the monkey and I don't know how to say it in English, I mean a bag or something. I mean you are carrying some, suppose that you are here. This is you, and this is the donkey or the ox or whatever, and this has some kind of luggage here. And the two things are actually connected by a rigid thing. Rigid, not elastic, nothing, okay? So this length here must stay fixed. I mean, you're not allowed to get it closer or farther. But then the donkey starts moving at uniform speed in this direction. It starts walking. Okay, so the question is, which is the trajectory of the luggage? Okay, you know, this was the kind of problems that's actually developed calculus. I mean, calculus was born to solve this type of things. And the tractrix, this actually is the curve.
Without gravity?
No. Here there is no gravity. You are on a field. You have your thing there with a stick, with a wooden stick, and you carry it. Okay?
This point.
Yeah. So it is the point described by your luggage on the field. Okay? This is called the tractrix, and actually that's it. This is it. Okay. I mean, okay, 5 minutes of history, because this adds nothing to the fact that if you rotate the tractrix, you get a surface of constant Gauss curvature. I mean, there's no. Okay. On the other hand, let me make just one other historical remark, which is important. This surface, it's true, it has constant negative Gauss curvature. On the other hand, it's really a bad surface if you look at it. This has an angle here. What I mean is that I cannot, and actually it stops here. I cannot, I mean, there is nothing like an infinite two-sided tractrix. Okay? So, this raised a very important question. I mean, this was not completely satisfactory when it was found, because the real question is there kind of a nice, complete, smooth surface with constant negative Gauss curvature in R3. Okay. The best thing you can do with the tractrix is actually to duplicate it like you do here. Okay. But if you do something like this, of course you are creating something which is not a regular surface, at least somewhere. Okay. So in fact, for a long time, the problem was, okay, this is nice, but is there something which does not have this problem? It's a complete surface of constant negative curvature, regular everywhere. And this is again one of the problems that Hilbert solved. It's not possible. In R3, they don't exist. Okay? So this is really as good as it gets. Okay? Having said all this, why I said all this, so now we have a model for positive curvature, a model for zero curvature, and a model for negative curvature. Good. Is there anything else?
So this A, constant A depends on the velocity.
Yes. Yes. Yeah, that would be kind of the velocity of your donkey, more or less. Or at least proportional to the velocity of the donkey. But now, the classification theorem is quite easy. we have all the tools to solve it quickly. So, and despite the fact that now the proof is quite simple, this is certainly worth calling a theorem. So, 1, a surface of 0 Gauss curvature. See, the only delicacy is how you phrase it. Because of course, if the output is a plane, then it's wrong. You know it. You have counterexamples. Okay. So the point is that it is not the plane. It's the best thing you can say is this. Okay. That's the best theorem you can hope. So, the surface of constant positive Gauss curvature. Again, you cannot say it's the sphere. But actually, of course, there is the obvious relationship between the Gauss curvature and the radius of the sphere. Okay, so if I say positive curvature A, that means that would be the sphere of radius 1 over square root of A. Okay, and then 3. Now we can state it. So a surface with constant negative. Is locally isometric. To a pseudosphere. Okay, so that's the best we can dream, and that's true. So, how do we prove it? The point is, first, in all cases, whatever surface we have, we use geodesic coordinates. Okay? So, the first fundamental form of any surface we are looking at will look like okay? So really everything boils down to the famous function g. And in fact, actually, I stopped the proposition before when we said in geodesic coordinates E is equal to 1, F equal to 0. But we actually know something about g. G, of course, cannot be fixed, but we know something. In particular, we know what? We know something on the curve. Remember, we start with the geodesic and then we construct this transversal line. On the geodesic, on the initial geodesic, we know also G. So in that language, remember that U was the parameter on the transversal geodesic, V was the parameter in the initial thing. So for U equal to 0, we are here, we are on gamma in the language before. So G of 0V is actually what? Well, that would be xv, remember? But v is the parameter on this geodesic, which is parameterized by arc length again. So this is equal to 1 for any v. Now, of course, what is not going to be true is that g of u, v, is equal to 1 in general. But at least for u equal to 0, yes, because it's this kind of skeleton curve geodesic is parameterized by arc length. okay? Plus, with the same trick of putting it somewhere, remember when we argued that then FU was equal to 0, then I can also prove that D in du, so GU, but again, only at 0V is equal to 0. Okay? Same trick. You put it in the right equation. Now you know a lot of stuff. You know E equal to 1 and F equal to 0. So these equations becomes extremely simple. But again, this conclusion will hold only on the geodesic. Okay. And now, just for notations, let's call G, little g, is not the coefficients of the second fundamental form. It's just to make the equations look like a bit nicer. So the square root. Okay, so this is something I know on any surface independently of Gauss curvature, whatever. So now, K is 1. So what does it mean that K is equal to 0? So K is equal to 0, of course, tells me what? That this expression here is equal to 0. This is the simplest one, of course, because of course this disappears too. So what I'm left really is that, so K equal to 0 if and only if the second derivative, and now I use this language here, if this function is constantly, the second derivative of this function is constantly equal to 0. But then I know a little bit how it looks like, no? Because then this means that G of u, G of uv, no, G is a function of two variables, no? And this is telling at least the behavior in the u variable. In the u variable is linear. Note that it's linear. In the coefficients will be functions of v, of which I know nothing. Okay, this equation is not yet strong enough to tell me the behavior in v. Okay, so this means I can write it as some function a of v, for which I know nothing, times u, plus b of v. Okay, for some functions a and b. But then I can use the initial data, I mean, the little I know, okay? So let's see, if I put u equal to 0, for example, let's use this. If I put, which of course translates into the fact that little g has the same property. So I put u equal to 0, this disappears, this tells me what? That b of v is actually equal to 1. Okay? Plus, again, I translate this equation, which again, this means that I take the derivative, this again, it's like saying the same thing for g, and this is telling me actually that a is equal to 0. Okay? So, the first derivative with respect to u is a. Okay? So, modulo checking that this changing of is not interfering with this. This implies actually, so these two conditions imply that actually g of uv was not just a linear function, but it was actually the constant function 1. Okay? Well, but then we are done. Then it's game over, because what is happening? E is equal to 1, f is equal to 0, and g is equal to 1, which of course implies what? Not that it is a plane, could be a cylinder, no? Could be something else, could be a ruled surface, could be anything, okay? But remember the proposition. Two things are locally isometric if and only if there is a chart which puts the first fundamental form in the same shape. Okay, but this is the shape of the first fundamental form of the plane, so this means that the geodesic coordinate map is an isometry. Okay? So this implies the plane, okay? And okay, the philosophy is always the same, so let's, now what does it happen if I take positive Gauss curvature? Positive Gauss curvature becomes this, no? So let me multiply, so this, let me call it a squared. So k is equal to a squared So I look at the formula, of course I multiply by g to the 1/2. So what I would prefer to write it as what? As the second derivative of g, of little g, in du squared is equal to plus or minus ag. Okay? A squared, sorry, a squared. I just said that it's squared. But then again, okay, actually I prefer to always to write it like this. Okay, so I can see this is the pendulum one. This is the harmonic thing. So this becomes what? The fundamental solutions. The fundamental solutions in U. So again, so this will be a linear combination of cos and sine with coefficients functions of V. Okay, so this implies again G of UV is equal to A of V cos AU. Actually here I have to remember there is this A here, so plus B of V sine AU. Okay. And then again, I just go and look at the effect of the two initial data here on this function. So for example, if I put u equal to 0, of course, this becomes 1, this becomes 0. So I'm left with a, so in particular this implies that a is not there. A is equal to 0. Then I play the same game. I take the derivative with respect to u, just a bit careful about taking the square root, and I find out also what is the coefficient. Actually, I find that b is equal to, sorry, b is 0 and a is 1. Okay, so I find, at the end, what I really get is that g. Okay, so g. Let's write that. So these equations immediately imply that g of u is equal to cos a. Okay, and then again, so now the question is, E is equal to 1, F is equal to 0, and the capital G, now let's write it with the capital G. Capital G is cos squared AU. Good exercise for you, because now I'm now realizing that we have never done it. Have we ever computed the first fundamental form of the sphere? Have we ever found a map, a parameterization of the sphere, which was giving actually this first fundamental form? I don't remember. Probably not.
Yes, I never see this.
Very good. That's a beautiful moment to give you an exercise. Okay. Actually, you know, in fact, the exercise it's always the first minute, no? Because actually, you even know which parameterization is this one. This is the you know the geodesics. This I remember. You know the geodesics on the sphere, and you know that this is the system of geodesic coordinates. So basically, you just have to write down the system of geodesic coordinates for the sphere. But you know the geodesics, so. In fact, it's this one. Okay? So you can rephrase, it's just a rephrasing. You don't have to do any computation. Okay? And then 3. Well, 3, now you understand the philosophy. If k is equal to minus a squared, then this equation becomes the same, but with the minus. Okay? So we have d2g du squared minus a squared g, and then what equal to 0. And then what do you get out of this? That this is a linear combination of sine and cos. You play the same game and you end up with the one of the pseudosphere. Okay? And again, remember that at the end, the conclusion always come out of the famous theorem we proved at the time we spoke about isometries. So all these things are proving that these coordinates put the first fundamental form in the same position as the corresponding one of the pseudosphere, or the sphere, or the plane. So the final conclusion comes from the fact that if this happens, the two things are locally isometric. Okay? There is a specific theorem we proved. Okay, in fact, we were thinking to this situation. Okay? Okay, so this is actually the final theorem I think I wanted to prove on for surfaces in R3. So from next time we will speak about differential geometry, really. Okay, so finally the course is starting. Okay, so now, it's impossible to study differential geometry without understanding what's going on in the only case where you can draw pictures. I mean, from now on, from next Tuesday, pictures will be completely stupid. I mean, we're going to draw 25-dimensional spaces, okay, which actually are not because actually the picture is the fact that you are drawing a picture means that you are thinking of something inside something else, at least the blackboard, at the very least. Okay, so differential geometry is precisely where you are not supposed to do that. Okay, so that's why without a good course on surfaces, you cannot really understand what's going on in differential geometry. So since we are left with just with 10-15 minutes, let's make an exercise. I feel we have done not many. So, so let's see, for example, there is a classical set of surfaces that are useful to know. And actually, in fact, all the three models ones that we have just seen fall into the category of surfaces of revolution. So what does it mean, surface of revolution? Surface of revolution means you actually, there is a curve, there is a special curve, and your surface is obtained by rotating this curve around some line. Okay? So you see the plane actually it's like this, because it's the rotation of a line through the normal line of the plane. The sphere is, of course, the rotation of half equator along the central axis, and we just saw why the pseudosphere is a surface of revolution. So let's play a little bit in general with surfaces of revolution. The catenoid is another one. They appear often. So let's see if we, for example, we can study some geodesics on that. So first of all, what do I mean by a surface of revolution? Actually, contrary to the case of the tractrix I just said, usually one decides to rotate along the z-axis. So let's look at surfaces which are parameterized in the following way. So for which there are two functions that I call f of v. I decide that v is this is the same. No, I think it was actually also this is the opposite. We called u the parameter on the tractrix and v. So I'm doing exactly the opposite just for your fun. Okay. So I'm taking the curve in the And now, of course, by this, what I really mean, I should have some domain of definition of this object. So let's say, first of all, in order to make sense, since I'm rotating now, this is rotating along the z-axis, the assumption is that, of course, f has to be a positive function, does not have to touch. And then, well, u is the angle of rotation, so you can decide where you want to put the angle. Let's say we do this. Of course, this would leave one curve out, but again, the same map with a different domain is also covering the curve that is missing. So there is no R. And then actually, where is V? Well, V I don't know. I'm taking some piece of a curve in the plane. So let's say that V actually varies between A and B, or actually, strictly speaking, should be an open set. Okay. So very good. So once this is set, let's compute the first fundamental form. So E So, now in fact, probably we have time to do everything. So let's compute everything. So suppose we want to know first, second, geodesics, everything. So XU is of course minus F. I drop a little bit, I drop the dependence, okay? F cos U, 0. XV,
Sine. Minus F sine.
I'm taking the derivative minus sine. Then XV, it's F prime cos, F prime sine, G prime. XUU, XUV, XVV. XUU is minus F cos minus F sine. XUV. XUV is minus F prime sine F prime cos 0. XVV is this with respect to V. I'm not sure I took the derivative of the right line. So XU is this, then I take the derivative with respect to V. Yeah, seems okay. So, okay, something I can, well, let's compute also the normal vector, or at least one normal vector. So it's XU cross XV. So this becomes F G prime cos U minus plus F G prime sin U minus F prime. And then everything is normalized. Okay, I don't even write what's on the denominator. Okay, it's the sum of the squares up to the power 1/2. And now E. E, F, and G. F squared. Zero. Every time you are lazy, you pay the price. Let's do it because actually I will need it in some formula. So what do I have here? Actually, F is everywhere. So I can erase it because everything is multiplied by F. So this becomes F prime squared plus G prime squared to the power 1/2. Okay. No, I'm just a bit, I don't remember at which moment I want to decide that I'm rotating a curve which is parameterized by arc length. You see how much it would simplify my life? What is the norm of the tangent vector to the curve which is rotating? Is exactly F prime G prime. So the tangent vector is exactly F prime G prime. So this is actually, this would become 1. This would become 1. I mean, everything would become much, much simpler. I just don't remember when I want to do it. Okay, let's not do it. So we can write everything in general and then remember that eventually everything will be much, much simpler if you assume that you are rotating a curve which is parameterized by arc length. So how much is little e? Little f and little g. Now, of course, no confusion between f, g, okay, and the functions which are rotating. Okay, n xuu. this becomes minus fg prime cos squared minus fg prime sine squared, so it's minus fg prime. Little f, oh sorry, divided by, okay, when I divided by the denominator of that. Little f is minus f prime g prime plus f prime g prime 0. Little g is f double prime g prime cos squared, f double prime g prime sine squared, so it's f double prime g prime minus f prime g double prime. Okay. Okay, out of this, of course, you can write down immediately Gauss curvature, mean curvature, right, immediately. It's a long formula, but you have everything now on the blackboard. So you can write K, H, K1, K2. Because remember that once you know K and H, you use the K1 is equal to H minus, okay, you have the formula. So in principle, I could write down everything. What do I want to get out of this? Let's compute, let's go to geodesics, which is kind of the most delicate thing, okay? So how does the system, the geodesic system look like now? Remember, it's d in dt e u dot plus f v dot equal to 1/2 blah blah blah. No? But actually, let me rewrite it. So it's d in dt e u dot plus f v dot is equal to 1/2 eu dot squared plus twice fu u dot v dot plus gu v dot squared. Then there is the symmetric equation for f u dot plus g v dot is equal to 1/2 ev u dot squared plus twice fv u dot v dot plus gv v dot squared. Okay, so this is the system of equations we are looking for. So in order to write them down in this case, of course, I need to compute all these derivatives of the coefficients of the first fundamental form. So this implies what? That EU, so actually this now it's good to remember that these are all functions of V. So of course EU, FU and GU are equal to 0, which is always very good news. EV is equal to FF prime. Of course, FV is equal to 0, and GV if I didn't assume anything, GV is twice F prime, F double prime plus G prime, G double prime. Okay? So how does the system look like now? So this becomes, the first equation is the nicest one, because of course f is 0 and here everything disappears. So what I'm really left with is d in d t of what? Of f squared times u dot is equal to 0. Okay, so this is the nice one, and then there is the bad one. Here not too much happens, so besides f equal to 0, I just have to replace these things. So where is my 1/2 gone? So let's see. Let's write everything. So this is G, so f prime squared plus G prime squared V dot. This is just G V dot. this has to be equal to 1/2 times what? So this is not there. And then what else? EV is equal to twice F prime U dot squared plus GV, which is another twice, so I can cancel everything and then cancel the 1/2. GV, it's F prime, F double prime plus G prime, G double prime, V dot squared. Okay. Now, I can tell you, writing down the solutions of these equations for any f and g is completely hopeless. I mean, it's impossible. So the way to understand a little bit what's going on is to proceed just by case with a little bit of help from geometry. Okay? So for example, where can I erase something? I don't know, probably here. We are rotating, remember, we are rotating in the xy plane. We are rotating around the x-axis something. So let's suppose we are rotating something like this. So on a surface of what I'm trying just to now, on a surface of revolution, there are clearly two types of special curves, okay? Which are, of course, the parallels and the meridians, for example, okay? So let's see, meridians. Meridians means the curves which are rotating, okay? So, for example, the initial curve, the one which generated everything. In our parameterizations, meridians corresponds to what? To u equal to a constant. So I'm freezing the angle and I'm keeping the profile of the curve for a given angle. Okay? So meridian means u is equal to u naught fixed and v. And now finally let me assume v V, now I want to think of V as V of S, where S is arc length. So actually this is a bit different from what I was saying before. So it's not V which is the arc length parameter. No, it's V of S will be a function. Okay. Now, what does it happen if I start assuming this? Let me call this equation 1 and this equation 2. Of course, equation 1 becomes obvious, no? Because u dot is equal to 0. So whatever is f, this equation is 2. Now the claim is that also 2 is okay. But why, how do we argue that? Okay. Let's use the arc length condition. So what do we really know? So we know, how do I phrase this, this assumption here? Is that, of course, I'm saying that 1 is the norm of gamma dot of x. So now I'm calling the curve which is rotating gamma, and I'm thinking of it as parameterized by s. Because it was parameterized by v, which is a function of s. So it's parameterized by s. So this is what? This is u dot xu plus v dot xv, so this is the computation we did already many times. So this becomes e u dot squared plus twice f u dot v dot plus g v dot squared. Okay, so this is just well, to the power, in fact, let's compute naught squared. So, right? Okay, so this implies what? On this special curve, of course, u dot is fixed, u is fixed, so u dot is 0. So this disappears, and this is just saying what? That G that we know, G is here, for sure, I didn't erase it. So what kind of equation is this in terms of the functions f and g? This is saying that f prime squared plus g prime squared, this is g, times v dot squared, this is equal to 1. Okay? Of course, how do I manipulate this? I say that this implies, this is of course the same thing. This is non-zero, because anyway, this is the norm of the tangent vector, okay, of the curve, so I'm assuming I'm rotating a regular curve. So it's moving anyway, so this I write it as, I can divide by that. So this becomes 1 over f prime squared plus g prime squared, and then I take a derivative with respect to s of this. Okay? So this implies what? That 2 v dot v double dot is equal to what? Okay, is equal to minus f prime squared plus g prime squared, squared. And then on top, what do I get? I get twice f prime, f double prime, plus twice g prime, g double prime. But these are the derivatives with respect to v, so maybe I hope I'm not confusing you. When I take these dots are the derivative with respect to s, and these slashes are derivative with respect to v. So here I'm actually using chain rule. Okay, v is the parameter that I used here to do all these computations. And now I'm thinking of v as a function of s. Okay. Okay, so why do I like it? Because of course v dot cannot be 0. Because already u dot is 0. So if also v dot is 0, then nothing is moving and this is not a curve. Okay? So I can divide by v dot. And I can also divide by 2 if I put the brackets in the right position. Okay? So this equation simplifies. Well, and actually simplifies exactly to this, okay? I'm not even, write it down. Write it down, multiply on both sides for what you have to multiply, and you get this equation here. Okay, there's nothing to learn here. Because actually time is over, so let me just say, in the same way, so all these things are geodesics. All these curves which are rotating are geodesic. Think to all the examples that you can think of. I mean, for example, for the plane, you are just saying, what are you rotating? You are rotating a segment, half line, no? Okay, every half line is a geodesic. Good. On the sphere, what are you rotating? Half equator. Okay, every half equator, wherever you put it, is a geodesic. Good. I mean, everything is big. Now, the other, of course, the other simple families of curves here would be the opposite. Now we fixed u and v was moving. Do the opposite, fix v and let u move. So these are circles, these are always circles, but put a different height on your surface. Are they geodesics or not? Comment I made of checking on the examples you know is because on the examples you know already the answer. In the plane, if you rotate a half line and you take a circle, is this a geodesic? We know which are the geodesics of the plane, no? Nice. So the question is the circle aligned? This means it's time to go to a coffee. Take a coffee. No, the circle is not aligned, so it's not a geodesic. I mean, okay? On the sphere, what is this question on the sphere? if you take actually these are called the parallels, of course. No? Is every parallel a geodesic? No, we proved that geodesics are only the great circles. And of course, there is only one great circle among parallels. Okay? So in fact, the answer has to be no. It has to be sometimes yes, sometimes no. Okay? And in fact, actually, the examples of the sphere tells you exactly the if and only if. All right? I leave you as an exercise. Just write down the corresponding system. This time it will be U dot which disappears, and you are left with V dot. Okay? You write down the system, and you see, and you have to prove what? That something, a parallel is a geodesic, if and only if the tangent vector to the curve at that point that you are rotating is parallel to the rotation axis. In our convention, the rotation axis was fixed to be the z-axis. So basically what you have to find in this, once it's set up in this way, what you have to prove is that the parallel is a geodesic if and only if the tangent vector to the curve is vertical. Okay? It's a manipulation of the equation. Okay. So yes, I think we are really done with surfaces, and so next week we will move to manifolds, okay?